You've probably come here to wind down, to let your breathing slow, to let your thoughts drift gently into the quiet spaces of the evening. Perhaps the day has been long, and you're searching for something calm, something to settle your mind as darkness falls around you. You're in exactly the right place. Tonight's journey takes us to the realm of stars, those ancient fires burning in the cosmic dark. But not to an ordinary star. Tonight, we explore something remarkable, something that astronomers discovered and immediately questioned. A star so massive, so impassable that physics itself seems to have been defied. We're going to explore a cosmic mystery that whispers a gentle truth. The universe is always stranger, always more wonderful than our current understanding suggests. Now, before we drift too far into stellar mysteries, let me tell you this gently. You don't need to understand astrophysics to enjoy this journey. All you need is curiosity and perhaps a comfortable pillow. Before we begin, I'd love to know where in the world you're listening from. It always touches my heart to see these quiet explorations reach listeners in so many corners of the globe. All of you settling in together to contemplate the mysteries above. If you enjoy these calm deep dives into science and wonder, please give this video a gentle like and subscribe to the channel. It truly helps others discover this peaceful corner of the internet where we explore the cosmos together. To those already subscribed, thank you from the depths of my heart. Your support means the world. Please do click the notification bell so you won't miss the next quiet adventure we take together into the unknown. I do hope this video isn't so fascinating that it keeps you awake. But if it does, at least you'll drift off, having learned something quietly wonderful about the most massive stars in existence. So, settle in, relax, let your shoulders drop, and allow your mind to float gently outward, toward the distant stars and the mysteries they hold. Let's begin tonight's exploration. What would it mean if you discovered something that contradicted everything you believed about how the world works? Chapter 1. Introduction: The Impossible Star. Let's drift gently into the story of a discovery that defied expectation. A star so massive, so improbable, that when astronomers first calculated its weight, they had to double-check their measurements. The story begins not long ago, in the realm of modern astronomy. Telescopes scattered across our planet and floating in space have given us the ability to see stars in distant galaxies, to measure their properties, to understand their nature. One such star was found in a galaxy called the Large Magellanic Cloud, a satellite galaxy that orbits our own Milky Way at a distance of 160,000 light-years. There's something profound about the moment when observation contradicts theory. It reminds us that nature is always more subtle, more complex, more magnificent than we imagine. This star became known as R136A1, a designation that sounds technical but carries within it a message. Here is something unexpected. Think of it like discovering a person who is 10 feet tall in a world where the laws of physics say nothing can grow taller than 7 feet. The person stands before you, undeniably present. The laws seem unchanged, yet something isn't quite right. The puzzle demands explanation. R136A1 is estimated to have a mass approximately 260 times that of our Sun. 260. Let that number settle gently into your mind. Our Sun, the star that has warmed our planet for billions of years, is a massive object. Yet this monster star outweighs it by a factor that seems almost impossible. The star is not just massive, it's extraordinarily bright. It shines with a luminosity millions of times greater than our Sun. Imagine standing beside a candle, then moving back 1,000 miles and being able to see that candle clearly. That's roughly the brightness differential we're discussing. The light from this star is so intense that it floods its surrounding region with radiation. Yet here's where the gentle paradox begins. Physics tells us there should be a limit to how massive a star can become. The more massive a star, the hotter its core, the faster it burns through its fuel. A star of such extreme mass should burn so ferociously that it tears itself apart, shedding its outer layers into space within a relatively short time. It should not be able to achieve such enormous mass in the first place. Yet this star exists. It floats in space, massive and burning, a testament to something we don't fully understand. Perhaps that's why this discovery resonates so deeply. It reminds us that the universe delights in complexity, that nature contains hidden mechanisms we haven't yet discovered, that there's always more to understand about how the cosmos works. We thought we knew the rules. The universe smiled gently and showed us an exception. In that exception lies invitation to look deeper, to question, to refine our understanding. Chapter 2. Stellar mass, the weight of fire. Now we turn to understanding what it means when we speak of a star's mass, and why mass matters so profoundly for stellar behavior. Mass is the fundamental property that determines nearly everything about a star's life. It's not how big the star appears, but how much material it contains. A star can be large, but less dense, or compact, but extraordinarily heavy. Mass tells the deeper story. When we measure the mass of distant stars, we use a gentle technique based on orbital mechanics. Imagine two dancers, one heavier than the other, orbiting around their shared center of gravity. The heavier dancer pulls more strongly, and the lighter dancer has to move faster to maintain the balance. By watching how stars orbit each other if they vary in binary systems, astronomers can calculate their masses from their motions. Think of it like watching two children on a seesaw. If one is much heavier, the balance point shifts toward them. You can calculate their relative weights by observing where they must sit to achieve balance. Stars work similarly. Their masses revealed through the mathematics of orbital motion. Our Sun has a mass that we use as the standard measurement. We call it 1 solar mass. When astronomers discovered this monster star, Era 136A1, their calculations showed it possessed approximately 260 solar masses. For comparison, most stars in our galaxy have masses between 0.1 and 10 solar masses. Anything above 20 or 30 solar masses is considered exotic, rare, unusual. 260 solar masses exists in a realm so extreme that it challenges our understanding of stellar formation itself. How does such a massive object even form? Gravity draws material together from collapsing clouds of gas and dust. But there should be limits. The radiation pressure from the star's core should push material outward, eventually stopping the accumulation. It's a bit like trying to pile water on top of water. Eventually, the weight of upper layers causes the lower layers to spread outward. You can't simply keep adding more and more water to a single column. Physical principles limit how tall you can make it. Similarly, there should be limits to how massive a star can become. Yet this star exists, defying those limits. In its existence lies a question that drives astronomy forward. What mechanism allows such objects to form and persist? The measurement of this star's mass came from careful observation and calculation, not from guesswork. Astronomers used spectroscopy, analyzing the light to determine surface temperature and brightness. They used orbital mechanics, watching how the star moved relative to its companions. They used multiple independent methods, all converging on the same improbable conclusion. There's something quite beautiful about the moment when science reaches the edge of understanding. The measurements are solid, the calculations are correct, the observations are clear. Yet the result seems impossible. That gap between observation and expectation is where discovery lives, where understanding deepens, where mysteries invite us to reconsider. Perhaps the universe is teaching us that we haven't fully understood how stars form. Perhaps there are mechanisms at work in the early universe, in dense stellar nurseries, that can build objects more massive than our theories predict. Perhaps the limits we calculated are not absolute laws, but merely the boundaries of our current knowledge. Chapter 3. Stellar Formation. Building stars from clouds. Let's drift deeper into understanding how stars form. The process that should prevent monsters, like R136A1, from ever existing. In the vast, dark clouds between stars, something extraordinary happens. These clouds, composed primarily of hydrogen and helium, with traces of heavier elements, are not motionless. Gravity acts upon them. Where the density is slightly higher, gravity's pull is slightly stronger. Over millions of years, this subtle force works its patient magic. Imagine a vast, dark garden where seeds of gravity are sown. Small irregularities places where the cloud is denser begin to attract more material. Gas falls inward, slowly at first, then faster as gravity strengthens. The cloud begins to collapse, pulling itself inward under its own weight. As the cloud collapses, it heats up. Gravitational potential energy converts to heat. The collapsing material warms. Eventually, if enough material accumulates, the core becomes hot enough for nuclear fusion to ignite. Hydrogen begins fusing into helium, releasing tremendous energy. A star is born. Think of it like compressing a spring. As you squeeze it, you store energy. Release the spring, and that energy escapes. Stars work similarly. Gravity compresses material, and that compression creates the heat necessary for fusion to begin. But here's where the paradox of massive stars becomes clear. As a star's mass increases, its core becomes hotter and hotter. The pressure from fusion reactions increases. This pressure pushes outward, resisting gravity's inward pull. At some point, the balance tips. The radiation pressure becomes so intense that it prevents more material from accumulating. Theory predicts this limit occurs around 120 to 150 solar masses. Beyond that point, a star should lose material through stellar winds. Radiation pressure becomes so intense that it literally blows away the star's outer layers. The star should be unable to grow larger. It should shed material faster than gravity can pull more in. Yet R136A1 exists at 260 solar masses. It has somehow passed through the theoretical limit and continued to exist as a coherent star. This is the gentle puzzle that defies explanation. One possibility is that, in the dense stellar nurseries, where such massive stars form regions, with thousands or millions of stars crowded together, the normal rules might not apply. Perhaps in these extreme environments, multiple massive protostars can merge together, combining their masses into even more massive objects. Perhaps collisions between forming stars create opportunities for mass accumulation that wouldn't occur in quieter stellar neighborhoods. Another possibility, perhaps the early universe, shortly after galaxies first formed, had conditions fundamentally different from the quiet regions we observe today. Perhaps higher densities, different compositions, or different physics allowed more massive stars to form back then. Perhaps what we see in the Large Magellanic Cloud is a relic from an earlier cosmic epoch. Or perhaps, and this is whispered, most softly perhaps, our understanding of stellar physics itself needs refinement. Perhaps there are mechanisms we haven't discovered, subtle processes we haven't yet modeled correctly, that allow stars of greater mass than we calculated. In that uncertainty dwells the true beauty of science, not the comfort of known answers, but the honest exploration of mysteries. The universe presents us with data. We must sit with that data, think about it carefully, and allow it to reshape our understanding gently, patiently, like water wearing away stone over eons. Chapter 4. Stellar Winds. The Outward Breath. Now, we turn to one of the most violent yet beautiful phenomena associated with massive stars. Stellar winds, the continuous outflow of material that should prevent monsters from forming. All stars produce winds. Our sun sends out a gentle breeze of charged particles. The solar wind that extends throughout the solar system. For most stars, these winds are relatively subtle. But for the most massive stars, stellar winds are anything but subtle. They're torrential outflows of material, moving at thousands of kilometers per second, carrying away millions of tons of stellar matter each second. Think of it like a star breathing. Our sun breathes gently, its outward breath barely noticeable. A massive star, by contrast, breathes with tremendous force. Its exhalation would knock you backward if you were foolish enough to stand anywhere nearby. The star continuously loses its outer layers to these winds, slowly shedding material back into space. The cause of these winds is radiation pressure. The intense light and radiation from the star's hard core pushes outward on the star's atmosphere. For massive, hot stars, this radiation pressure becomes so great that it overcomes gravity's inward pull. The outer layers can't be held in place. Material is driven outward at tremendous velocities. Imagine standing at the base of a waterfall, with enormous pressure pushing you away. No matter how hard you try to hold your position, the force eventually wins. You're swept backward. Material near a massive star's surface experiences something similar. The radiation pressure overwhelms gravity's grip, and the material is blown away. Picture sheets of material streaming outward from the star's surface, glowing softly with the light of their parent star. The wind carries these ghostly sheets into space, where they eventually dissipate into the interstellar medium. Over time, a star loses significant portions of its mass through these winds. The relationship between mass and stellar wind is crucial. The more massive the star, the hotter its surface, the more intense its radiation, the more violent its winds. It's a self-limiting process. The most massive stars blow themselves away most rapidly. They should lose their excess mass before they can become too large. Yet R136A1 has somehow retained its enormous mass despite the tremendous stellar winds it must produce. This is another layer to the paradox. Not only did the star manage to form at such an extreme mass, but it has also resisted being blown apart by its own fierce winds. One explanation might be that the star is younger than most estimates suggest. If it recently formed, perhaps through merger or unusual circumstances, it hasn't yet had time to lose significant mass through winds. Perhaps it's in a brief window of existence before stellar winds gradually tear it apart. Another explanation. Perhaps the star's binary companion, it's not alone in space, plays a role. perhaps the gravitational interaction between the two stars somehow helps maintain the monster star structure, resisting the tendency to be blown apart. There's something quite poignant about imagining this star. It breathes so fiercely, loses so much material, exists in such a violent state that it cannot possibly endure for very long. By cosmic standards, this star is doomed. Its days are numbered. In a few million years, it will collapse, explode, and return its material to the cosmos. Yet for now, in this moment, it burns brilliantly, a testament to the universe's strangeness. Perhaps that's why this star matters to us, not because it defies our theories, though it does, but because it reminds us that existence is temporary, that greatness is often brief, that the most spectacular things often burn out quickly. In that recognition lies a gentle melancholy, a quiet acceptance of impermanence. Chapter 5. The Eddington Limit. The barrier that shouldn't be crossed. Let's turn now to one of the most fundamental limits in stellar physics. The Eddington Limit. The theoretical barrier that R136A1 appears to have surpassed. In 1924, Arthur Eddington, a brilliant British astrophysicist, derived a mathematical relationship that would become fundamental to our understanding of massive stars. He calculated the maximum luminosity that a star of a given mass could have before radiation pressure exceeded gravitational force. Beyond this limit, the star couldn't hold itself together. Material would be blown away faster than gravity could retain it. The Eddington limit depends on the star's mass. More massive stars can have higher luminosities while remaining stable. But there's still a ceiling. For a star to grow very massive, it must increase its mass while its luminosity approaches but doesn't exceed the Eddington limit for that mass. Think of it like a tightrope walker with increasing weight. A lighter person can walk with greater abandon on a thinner rope. A heavier person needs a thicker, stronger rope and must move more carefully. The Eddington limit is the point where the rope can no longer hold the person's weight, no matter how carefully they walk. The relationship between mass and the maximum possible luminosity creates a natural limit on how massive a star can become. A star trying to grow to extreme masses runs into the problem that its luminosity increases faster than the Eddington limit allows. At some point, the star can't grow anymore without violating the fundamental balance between gravity and radiation pressure. Theory suggests that stars can't easily exceed 120 to 150 solar masses. Beyond that, the Eddington limit becomes a hard barrier. The star loses mass through winds faster than it can accumulate new material. Growth stops. The star either sheds excess mass and stabilizes at a lower mass, or it becomes unstable. Yet R136A1 exists at 260 solar masses. It appears to be operating above the Eddington limit, not just barely, but significantly above it. This is the heart of the paradox. The star shouldn't exist. Physics says it can't. Yet, there it is, burning in the cosmic dark, defying the laws that should govern stellar behavior. One possibility is that our calculations of the star's properties are slightly off. Perhaps it's not quite as luminous as we calculated. Perhaps it's not quite as massive. Perhaps better measurements would bring it below the Eddington limit threshold. But multiple independent observations have been made, and they all converge on the same conclusion. The star really does seem to be this massive and this luminous. Another possibility. Perhaps the Eddington limit itself requires refinement for extremely massive stars. Perhaps the simple calculation that works well for ordinary stars breaks down in extreme regimes. Perhaps there are quantum effects, relativistic effects, or other phenomena we haven't accounted for that change how the limit operates. Picture a rule that works perfectly for everyday objects, but breaks down when you apply it to extreme cases. We see this pattern throughout physics. The rules of everyday mechanics work beautifully until you approach the speed of light. Then relativity becomes important. They work until you get to atomic scales. Then quantum mechanics matters. Perhaps the Eddington limit has similar hidden complexities. There's something quite beautiful about discovering that a fundamental principle has limitations we didn't expect. It's not that the principle is wrong, it's that our understanding of how it applies is incomplete. The universe is always richer, more nuanced, more subtle than our theories capture. Perhaps the lesson is humility. Perhaps R136A1 is the universe's gentle way of telling us, you understand some things, but not everything. Keep looking, keep questioning, there's always more to learn about how nature works. Chapter 6. Stellar Evolution. The brief, brilliant life now. We turn to how the life of such a massive star unfolds, knowing that it will be short and brilliant. Stars are not eternal. They are born, they evolve, they age, and eventually they die. The most massive stars follow the same pattern, but accelerated dramatically. Where our Sun will live for approximately 10 billion years, a star like R136A1 will live for only a few million years. The greater the mass, the faster the consumption of fuel, the shorter the life. Imagine a candle that burns with the brightness of 1,000 normal candles. It will burn out far more quickly. The more intense the flame, the faster the wax is consumed. Massive stars work similarly. Their intense burning means they exhaust their nuclear fuel much more rapidly than lower mass stars. Think of it like living life at maximum intensity. Every moment burns more brightly, but the total time is brief. A massive star spends its youth period of millions of years fusing hydrogen into helium in its core, burning with incredible intensity, but eventually, the hydrogen fuel in the core is exhausted. The star enters a new phase. When a star's core runs out of hydrogen, it begins fusing helium into heavier elements. This phase is shorter, more violent. The star's structure changes. Its outer layers expand. The star becomes a red supergiant, bloated, dying star, approaching the end of its life. For a star like R136A1, this phase would be dramatic. The star would transform, its atmosphere expanding, its winds becoming even more violent, shedding material at even greater rates. It would drift through space, still brilliant, still burning, but clearly approaching its end. Eventually, the core runs out of helium. Then it fuses heavier and heavier elements: carbon, oxygen, silicon, iron. Each phase is shorter, more intense, more violent. The star becomes increasingly unstable, more and more desperate, as it tries to maintain the fusion that holds it up against gravity's relentless pull. Finally, when the core reaches iron, the end comes. Iron does unfuse into heavier elements through normal nuclear reactions. The process would consume energy rather than release it. At this point, gravity wins. The iron core collapses. The outer layers fall inward. The pressure and temperature in the core reach extremes beyond imagination. And then, explosion. The star dies, not quietly, but catastrophically. A supernova erupts, one of the most violent events in the universe. The star's entire outer envelope is blown away at tremendous velocities, 15,000 kilometers per second or more. The energy released in this explosion outshines billions of normal stars. For a brief moment, the dying star shines as brightly as an entire galaxy. What is left behind is either a neutron star, a city-sized sphere of matter so dense that a teaspoon would weigh as much as a mountain, or a black hole, depending on the star's final mass after its life's work is done. Yet, here's the gentle tragedy of R136A1. This star is likely quite young. Astronomers estimate it might be only a few million years old. Perhaps 2 or 3 million years have passed since its birth. It looks toward a future measured only in millions of years remaining. Sometime in the relatively near future, cosmically speaking, this brilliant monster will reach the end of its brief, brilliant existence. Perhaps that's why we're drawn to studying such stars. They remind us of mortality, of the impermanence of even the greatest things. The most massive, most brilliant, most powerful stars burn out first. Their greatness is measured in cosmic intensity, but their time is brief. There's a poignancy in that reality, a gentle melancholy that speaks to something deep within us. Chapter 7. Stellar Companions. A monster's relationship. Let's drift toward an important detail about R136A1. It doesn't exist in isolation. The monster star has a companion, and this relationship may be crucial to understanding how such a massive object came to be. Stars often come in pairs, sometimes in complex hierarchies of multiple stars orbiting one another in intricate gravitational dances. These binary or multiple star systems are common in the universe. They offer insights into stellar properties through the orbital mechanics that bind the stars together. R136A1 is part of a larger star cluster, a region packed with thousands of young, massive stars. It's also in a binary or multiple system with other stars nearby. These companions are also quite massive stars, with tens or hundreds of times the mass of our Sun. Yet R136A1 is the heavyweight champion, the most massive of them all. The presence of these companions might tell us something important about how R136A1 became so massive. In dense stellar environments, stars can collide. Two stars, drawn together by gravity, might actually merge, combining their masses into a single star. This process, while rare in the quiet regions of galaxies like ours, might be more common in the chaotic, densely packed regions where massive stars form. Imagine two massive stars orbiting each other in a tight embrace. Gradually, over millions of years, orbital mechanics causes them to spiral inward. Their orbits decay, the stars drift closer and closer. Eventually, they collide. The collision merges them into a single, even more massive star. Think of it like two raindrops falling through clouds, eventually merging into a larger drop. The universe does this with stars, at least in theory. Whether this actually happens frequently enough to create a star as massive as our 136A1 remains an open question. In the dense stellar nursery where our 136A1 formed, perhaps multiple mergers occurred. Perhaps the star we observe today is the result of several massive stars combining. Perhaps what we think of as a single star is actually the merged remnant of multiple stellar objects. If this is true, then our 136A1 represents something profound. Not a star that defies the limits of how massive a single star can become through normal formation, but rather a composite object created through stellar collision and merger. The individual stars might each have masses below the theoretical maximum, but combined, they exceed all expectations. This possibility is both more and less exciting than a star that simply breaks the rules. It's less exciting because it means the star isn't as mysterious. Merger explains it, but it's more exciting because it reveals a phenomenon, stellar merger, that reshapes how we think about star formation, especially in dense regions. The relationship between R136A1 and its companions reminds us of something important. In the universe, objects rarely exist in complete isolation. Everything is connected through gravity. Everything influences everything else. A star's mass might be determined not just by the conditions at its birth, but by the interactions with its neighbors over millions of years. Perhaps that's a lesson for us as well. We often think of ourselves as individuals, separate and independent. Yet, we're shaped by our relationships, by the people and circumstances around us. Our mass, metaphorically speaking, is determined partly by our interactions with others. We become who we are not in isolation, but in connection. There is something quite beautiful about that realization, that the most massive star we know may be massive, precisely because it wasn't alone, because it merged with others, because it benefited from proximity and interaction. It's a reminder that greatness is often built on connection, not solitude. Chapter 8. The birth of monsters. Where do extreme stars come from now? We turn to the broader question of how stars this massive form in the first place, and what conditions allow such extreme objects to exist. Star formation is a process that unfolds over millions of years, driven by gravity's patient accumulation of material. In regions of space where massive molecular clouds float, gravity slowly draws the gas together. The cloud fragments into smaller pieces, each piece collapsing under its own weight. As a fragment collapses, it heats up. If enough material accumulates in the center, temperatures and pressures become sufficient for nuclear fusion to ignite a star is born. The more massive the collapsing fragment, the more massive the resulting star. But here's the puzzle. Most star-forming regions produce a range of star masses, from very small stars to moderately massive ones. Really massive stars seem to be rare, and extremely massive stars, like R136A1, are rarer still. Something seems to limit how massive most stars become. One factor is the efficiency of fragmentation. When a giant molecular cloud collapses, it doesn't all collapse into a single object. Instead, it fragments into many smaller pieces. Each piece becomes a star. The more fragmentation occurs, the more small stars form, and the fewer massive stars result. The less fragmentation, the larger the individual pieces, the more massive the resulting stars. Picture a breaking wave crashing on a beach. The wave fragments into countless droplets. If you could control the fragmentation, producing fewer but larger pieces, you'd have fewer, larger droplets instead. Stars form similarly. Controlling fragmentation determines the resulting mass distribution. Think of it like dividing a cake. If you cut it into many small slices, you get many small pieces. If you cut it into few large slices, you get fewer, larger pieces. The size of the pieces depends on how you divide the cake. In star formation, gravity determines the cutting, the fragmentation. In the dense regions where our 136A1 formed, perhaps fragmentation was less efficient than usual. Perhaps the conditions were such that less division occurred, allowing larger pieces of gas to collapse together. Or perhaps massive stars formed first, and then grew even larger by accreting additional material or merging with other stars. The Large Magellanic Cloud, where our 136A1 resides, is a galaxy with somewhat different properties from our Milky Way. It has a different composition, different density in star-forming regions, different chemistry. Perhaps these differences make extreme star formation more likely. Perhaps in the LMC's star-forming regions, the conditions naturally allow more massive stars to form than we typically see in our own galaxy. Or perhaps R136A1 represents something even more fundamental: evidence that our understanding of how stars form and grow is incomplete. Perhaps there are mechanisms we haven't discovered, processes we haven't modeled correctly, that allow more extreme objects than our current theories predict. The universe seems to delight in pushing boundaries, in finding the edge cases, in creating exceptions to every rule we establish. R136A1 might be the universe's way of telling us, your models are good, but they're not complete. There's always more to discover. Always deeper levels of complexity. Perhaps the lesson is patience. Stars form over millions of years, driven by gravity's relentless accumulation. Massive stars form in special places, under special conditions, through processes we're still learning to understand. As we gather more observations, as we refine our models, as we look more carefully at star-forming regions, our understanding deepens. The universe doesn't reveal all its secrets at once. It whispers them slowly, patiently, inviting us to listen carefully and adjust our understanding as we learn. R136A1 is one such whisper telling us that star formation is more subtle, more complex, more wonderful than we knew. Chapter 9. Observations and measurements. How we know this star exists. Let's turn to the practical details of how astronomers determined R136A1's properties, and what challenges they faced in these measurements. Modern astronomy relies on careful observation and measurement. We can't touch distant stars, we can't visit them. We can only observe the light. They emit the light they reflect in from those observations, infer their properties. It's like being a detective who must reconstruct a crime scene from subtle evidence. For R136A1, the primary tool was spectroscopy, analyzing the light from the star. When light passes through a prism or through the slits of a spectrograph, it spreads out into its component wavelengths, like a rainbow. Scientists analyze this rainbow, identifying specific features that reveal the star's composition, temperature, and motion. Think of light as a message written in a special code. Different elements absorb or emit light at specific wavelengths. Hydrogen has its characteristic pattern. Helium has another. By reading this code, astronomers determine what the star is made of. But there's more complexity. The star's temperature affects how bright it is at different wavelengths. The star's motion, whether it's moving toward or away from us, shifts the light toward blue or red wavelengths through the Doppler effect. All of these signals are embedded in the light, waiting to be decoded. Imagine receiving a message written in code, distorted by noise, transmitted through a medium that alters it. The message is still there, but extracting it requires careful analysis, multiple checks, and sophisticated instruments. That's what modern spectroscopy does. For binary or multiple star systems, there's an additional technique: measuring orbital motion. If two stars orbit each other, their light shifts toward us. Blue shifted when moving toward us, and toward red when moving away. By measuring these periodic shifts, called radial velocity variations, astronomers can determine the star's masses. Newton's laws of motion allow us to calculate mass from orbital properties. If you know how fast a star orbits, and how long the orbit takes, you can calculate the masses of both objects. It's a beautiful application of centuries-old physics to modern astronomy. Picture a merry-go-round with two horses of different weights. The heavier horse pulls more strongly toward the center. By observing how the lighter horse is pulled, you can calculate the heavier horse's weight. Stars work similarly. Their gravitational pull reveals their mass through the orbital motion they induce. When astronomers applied these techniques to R136A1, they found a star with extraordinary properties. The measurements pointed to a mass around 260 times that of our Sun. But scientists understood that this measurement had some uncertainty. The true mass might be somewhat lower or somewhat higher, but the central value was clear. This star was genuinely, significantly, more massive than theory suggested should be possible. The observations came from multiple sources: ground-based telescopes and space-based instruments like the Hubble Space Telescope. Different techniques, different instruments, all converged on the same conclusion. The star is real. It is that massive. The consistency across multiple measurement methods increased confidence in the result. Yet scientists remained appropriately cautious. Astronomy is built on careful measurement and healthy skepticism. Just because a result is surprising doesn't mean it's wrong, but it does mean it demands extra scrutiny. Would further observations refine the measurement? Would improved instruments shift the estimates? These are the questions that drive further research. Perhaps that's why the study of R136A1 continues, not because the star's existence is in doubt, but because understanding it better, measuring its properties more precisely, offers insights into stellar physics that textbooks don't yet contain. The universe has shown us something unexpected. We're still working to fully understand what it means. Chapter 10. Deep Dive. The interior of an impossible star. Let's drift deeper into the interior of R136A1, exploring what conditions must exist at its core and how it maintains its improbable structure. At the heart of every star lies a region of such extreme conditions that human minds struggle to comprehend them. The pressure is billions of times greater than Earth's atmosphere. The temperature reaches tens of millions of degrees. In this crucible, nuclear fusion occurs, converting hydrogen into heavier elements and releasing the energy that makes the star shine. For a star like R136A1, these core conditions are even more extreme. The mass pushing down from above creates pressures beyond what we can create in any laboratory on Earth. The temperature is higher. The fusion reactions occur more rapidly. The star is, in every sense, at the edge of what's physically possible. Picture the center of a star like the heart of a violent storm, where all the fury of nature concentrates. The particles are moving at incredible speeds, colliding with tremendous force. Nuclei are fusing together, releasing energy that drives outward. The pressure and temperature creates an environment that seems almost alien, almost impossible. The incredible density near the star's core is difficult to visualize. A teaspoon of material from the core would weigh hundreds of tons on Earth. The material is compressed to such extremes that atoms are stripped of their electrons. Nuclei touch one another. The normal rules of chemistry don't apply. Only the laws of nuclear physics matter. Think of it like taking an enormous building and compressing it to the size of a grape. All that mass concentrated into an impossibly small space. The pressure and density at the center of a massive star achieve this kind of extreme compression with the force of gravity. Despite being the hottest, densest region, the core is actually where the star's fuel burns most efficiently. The higher the temperature and pressure, the faster the nuclear reactions. For R136A1, hydrogen is being converted to helium at a rate that dwarfs what occurs in our sun, where our sun converts about 600 million tons of hydrogen each second. R136A1 might convert thousands of times more. It's like comparing a candle's flame to a raging inferno. Both are combustion, both release energy through a chemical process. But the inferno is orders of magnitude more intense, consuming fuel at a rate the candle couldn't approach. Massive stars are cosmic infernos, burning with such intensity that their fuel is exhausted in millions of years rather than billions. The star maintains itself through a delicate balance. Gravity pulls inward with tremendous force, but the pressure and radiation from fusion push outward with equal force. The star is in hydrostatic equilibrium, perfectly balanced between inward and outward forces. This balance determines the star's size, temperature, and brightness. For R136A1, imagine this balance achieved at an extreme scale. The star's interior is a cauldron of such intensity that the mere fact of its coherence seems remarkable. Yet the mathematics works. The laws of physics, applied rigorously, suggest that such extreme balance is theoretically possible, though our experience with ordinary stars doesn't prepare us for anything like it. The star's opacity, how easily light can pass through its material, is crucial. Radiation produced in the core gradually works its way outward, being absorbed and re-emitted countless times as it diffuses through the dense material. This outward diffusion of radiation creates the pressure that balances gravity. Think of it like pressure building up in a sealed container. The hotter the contents, the higher the pressure. But in a star, if pressure builds too much, the star expands, cooling the core, reducing the pressure. If pressure drops too much, gravity pulls the star inward, heating the core, increasing the pressure. This feedback mechanism maintains balance. For the most massive stars, this balance is precarious. The slightest perturbation could tip the star into instability. Yet R136A1 persists, burning brilliantly, seemingly stable despite the extreme conditions. Understanding how it maintains this stability despite being so far from the typical stellar equilibrium point remains an open question. It's remarkable to contemplate, deep in space, billions of light years away. This star's core seethes with nuclear reaction. The fusion rate is staggering. The heat is beyond comprehension. Yet the entire process is orderly, governed by physics, following mathematical rules. From chaos to violent nuclear reactions emerges order, a stable stellar structure. Perhaps that's the lesson embedded in R136A1's interior. Even in the most extreme conditions, order is possible. Even when pushed to the edge of what physics allows, systems can achieve remarkable stability and coherence. The universe is capable of wonders that seem to exceed the boundaries of possibility, yet happen within perfectly natural physical laws. Chapter 11. Philosophy. What the monster star teaches us. Beyond the physics, beyond the measurements, R136A1 whispers lessons about knowledge, understanding, and the nature of discovery itself. What does it mean when we encounter something that defies our expectations? When the universe reveals an object that contradicts our theories, our models, our calculations? Is it a failure evidence that we've gotten something fundamentally wrong? Or is it an invitation, a gentle nudge toward deeper understanding? There's something profoundly human about building theories and models. We take observations, we recognize patterns, we construct explanations. These explanations feel solid, comprehensive, complete. We write them into textbooks. We teach them to students. We use them to predict future observations. It feels like we've figured something out. But then nature reveals an exception. Something appears that doesn't fit our framework. And in that moment, if we're honest with ourselves, we must admit something. Our understanding was incomplete. Not wrong, exactly, but partial. We had captured some truth, but not all of it. Think of it like understanding a language by observing everyday conversations. You learn the grammar, the vocabulary, the patterns. But then someone recites poetry, or sings, or tells jokes, and suddenly you realize the language is far richer, more subtle, more complex than you understood. Your knowledge was valid, but limited. R136A1 is the universe's poem, whispered in the language of stellar physics. It tells us that massive stars, how they form, how they live, are more complex than our textbooks suggest. There are phenomena at work that we haven't fully grasped. There are processes we haven't completely understood. Perhaps the most important lesson is humility. The universe is vast beyond our comprehension. It has had billions of years to evolve, to develop, to explore the boundaries of what's possible. We, with our brief observation time, our limited instruments, our incomplete theories, should approach it with appropriate humility. We understand some things, but there's always more to learn. We too face situations that challenge our understanding of how the world works. We make assumptions about people based on limited information, and they surprise us. We predict how events will unfold, and circumstances defy expectation. These moments are uncomfortable, unsettling. But they're also opportunities. They're invitations to expand our understanding, to reconsider our assumptions, to accept that reality is more complex than we imagined. There's something quite beautiful about that realization. It means the world is always more interesting than we think. There are always surprises waiting. There are always depths we haven't explored. Life, like the universe, is inexhaustible. R136A1 also reminds us about the nature of existence itself. This star is brilliant, massive, powerful. By every measure of cosmic importance, it's impressive. Yet it will die, and die soon. In cosmic terms, in a few million years, an eye blink in universal timescales, this mighty star will explode. Its matter will scatter to the winds. Its light will cease. The universe will continue without it. Yet during its brief existence, it serves as a beacon. Its light travels across space. It influences the galaxies around it. It shapes its environment through its powerful radiation. Its brief, brilliant life has meaning and impact, even though it's temporary, even though it ends. Perhaps that's a lesson for us as well. We are conscious creatures, aware of our mortality, aware that our time is limited. We'll age and die, and the world will continue. Yet during our existence, we matter. We influence those around us. We shape our environments through our actions. Our lives have meaning and significance, even though they're temporary. R136A1 is a cosmic mirror, reflecting back lessons about excellence and impermanence, about the power of intensity and the brevity of brilliance. It teaches that the most extraordinary things often burn out first. It reminds us that greatness is measured not by duration, but by intensity, by the brightness of the light cast during existence, by the depth of the impact made while burning. Perhaps the universe creates such extreme objects thus that shouldn't exist, that persist in impossible states, that burn with unimaginable intensities, so that we might contemplate them and learn. Learn about the nature of physical law. Learn about the limits of understanding. Learn about what excellence looks like in the cosmos. Learn about ourselves, reflected in the distant fire of an impossible star, closing the light that shouldn't shine. So here we are at the gentle close of our exploration of R136A1, the monster star that shouldn't exist yet does, burning brilliantly in the cosmic dark. We've drifted through the landscape of stellar physics, through the mysteries of massive star formation, through the paradoxes that emerge when observation challenges theory. We've contemplated the interior conditions of the most extreme stars, the brief and brilliant lives they lead, and the lessons they whisper to us across the distance of space and time. What we've discovered is not definitive answers, but deeper questions. Not certainty, but mystery. Not the closure of understanding, but its expansion. R136A1 stands as proof that the universe is always more subtle, more complex, more wonderful than our current theories encompass. We've journeyed together through the realm of stellar impossibilities, from the fundamental principles that should limit stellar mass, to the observations that have revealed a star exceeding those limits, to the various explanations scientists propose to understand how such an object came to be. Each step brought us deeper into mystery, deeper into wonder. Somewhere in the large Magellanic Cloud, 160,000 light-years away, this impossible star continues its brilliant work. Its massive furnace burns hydrogen at a rate that boggles the mind. Its winds roar outward at thousands of kilometers per second. Its radiation floods the surrounding space with light. It drifts among its companions, and slowly, over millions of years, it approaches its inevitable end. The light from this starlight that took 160,000 years to reach Uskari's information, from a place so distant that its light was ancient when our species was young. That ancient light tells us of an object that defies expectation, that exceeds the boundaries we thought were firm, that reminds us how much we still have to learn. There's something quite serene about contemplating such a distant, extreme object. It's so far away that it can't affect us. Its light reaches us as an observer reaches a work of art, appreciating it without being in danger from it. We can study our 136A1 safely, learn from it, marvel at it, without any direct impact on our lives here on Earth. Yet in another sense, that star is profoundly connected to us. The light we see was emitted before human civilization began. The material that makes up that star came from earlier generations of stars. Ultimately, the atoms that compose both the monster star and ourselves came from the same cosmic sources. We are all connected, woven from the same stardust, shaped by the same physics. As you drift toward sleep tonight, let R136A1 whisper to your half-conscious mind. Let it remind you that there are still mysteries in the universe. Let it tell you that the most extraordinary things often burn the brightest but burn the briefest. Let it suggest that we should embrace intensity, embrace excellence, embrace our own brief moment of brilliance before our own light eventually fades. The universe contains wonders that exceed our understanding. It contains exceptions to every rule we establish. It contains objects that seem impossible, yet persist. And in those impossibilities lies invitation to look deeper, question more carefully, expand our consciousness of what's possible. Thank you for this journey through the realm of extreme stars. Thank you for settling in with me as we explored the monster that physics says shouldn't exist, yet burns magnificently nonetheless. Your company on this quiet exploration means the world to me. If these calm investigations into the mysteries of the cosmos bring you peace, if they help your mind drift gently toward rest, if they remind you that the universe is a place of endless wonder, please continue to return to this channel. There are always more mysteries to explore, more wonders to contemplate, more quiet journeys to take through the cosmic deep. To those who've supported this channel, Your kindness and encouragement allow me to continue bringing these gentle explorations to you. Thank you for making this possible. Your support is felt and appreciated more than words can express. As you close your eyes tonight, picture this. Far across the cosmos, a star that shouldn't exist continues to burn. Its light streams outward in all directions, traveling through the void. Some of that light eventually reaches Earth. It passes through our atmosphere. It strikes our telescopes. It becomes data that tells us stories about the universe's complexity. And you, reading these words, are part of that chain. You are connected to that distant star through light and through the elements. You are made of the same matter that composes every star. You are, in a very real sense, stardust contemplating other stars. How remarkable, how wonderful. Sleep well, knowing that the universe is always more interesting, more complex, more beautiful than we imagine. Sleep knowing that there are still mysteries to solve, still wonders to discover, still truths waiting to be understood. Sleep knowing that somewhere in the cosmos, an impossible star continues its brief, brilliant journey through time and space. In that knowledge, in that wonder, in that gentle acceptance of mystery, there is peace. Until next time, when we drift together once more through the cosmos and all its infinite mysteries. Sleep well, friends. Sleep beneath the light of distant fire.